Hello everyone, I'm Neha Kashyap Agarwal. The research paper I have chosen is Deep Transfer Learning Across Cities for Mobile Traffic Prediction. It got published in the Professional Association IEEE in December 2021. The link is provided for your reference. I will be covering the following contents in my presentation. Mobile traffic refers to internet traffic which comes from a mobile device, typically smartphone, tablet, etc. Predicting it is important for intelligent network resource planning and proactive service provisioning. Existing approaches focus on training a well-performed model for cities with a large amount of mobile traffic data. For cities with scarce data, the prediction performance remains limited. To address this problem, a cross-city deep transfer learning framework for mobile traffic prediction (CCTP) is proposed. First, a special temporal deep learning model, GASTIN, is presented, which leverages recurrent neural networks. It is pre-trained with abundant data from a source city to obtain prior knowledge of mobile traffic dynamics. Then, an efficient cross-domain based, adapter-based generative adversarial network (GAN) is devised for distribution alignment. The data scarcity issue is addressed by an intercluster transfer learning strategy for performance enhancement. Experiments conducted on real-world mobile traffic datasets boost CCTP performance in citywide mobile traffic prediction with data scarcity issues. There is an explosive growth in mobile traffic demand. Mobile traffic prediction problem can be solved via statistical models like ARIMA and Holt-Winters exponential smoothing, but they only consider temporal relations in each region, ignoring important spatial correlation with the neighboring regions. Due to different levels of city development, like population density, the amount of mobile traffic between cities vary significantly. In a less crowded city like Trentino, the regions of mobile traffic demand are scattered and the traffic data is generally much scarcer. Adequate data is usually a prerequisite for deep learning based methods. Current researchers only focus on mobile traffic prediction tasks in cities with high development levels like Milan, leaving many other cities unable to benefit from the recent techniques due to data scarcity. So, how can a city obtain a remarkable prediction model in case of data scarcity? Through transfer learning. Mobile traffic pattern across cities may possess a certain degree of similarity. A model learned from scratch with insufficient data can fail to achieve good performance, so a good choice for a city with data scarcity is to reuse a well-trained model from a city with abundant historical data. The datasets used are publicly available. Milan is partitioned into 100 by 100 grid map of 235-meter width, while Trentino is divided into 6575 cells with a coverage area of 1000 meter into 1000 meter for each cell. Trentino is sparsely populated, so only a few regions have demands for mobile traffic. This possesses a great challenge for training a powerful traffic prediction model. Mobile traffic patterns in different regions across cities can exhibit high similarity. This could be useful for mobile traffic prediction in a data-scarce city. Data from different regions of Milan has a wide range of values and are mainly concentrated around 200 MBs. In Trentino, the range of traffic volume is relatively narrow and most values are less than 100 MB. Problem formulation is done as follows, where the objective is to learn a function f which can predict mobile traffic volumes. Existing methods utilize convolutional neural networks to capture spatial relationships based on a grid structure that fails to depict real spatial relationships. since it only regards geographically adjacent regions as neighbors but neglects the distant ones. Besides, they are not suitable for the city with irregular geographic. Therefore, it is required to construct a special relation graph. Traditional distance measures focus on numerical distance but ignore the structural difference and are not suitable to measure the similarity of two mobile traffic patterns. Dynamic time wrapping offers a modified distance metric with alignment and provides a better pattern match. Therefore, we applied DTW algorithm. Next, we further cluster nodes in a special relation graph based on the average usage of mobile traffic into C clusters, and then regions with similar volumes are grouped into one cluster. Then we propose a attention-based structural recurrent neural network. Subsequently, edges in the special graph are grouped into different types according to the combination of classes of the two connected nodes. The architecture of Gaston is shown here. For each cluster of nodes, there is a corresponding node RNN to capture node information, example, the temporal features of the node. Likewise, for each type of edge, there are edge RNNs to extract edge information, special features. Here, LSTM is adopted as the time series module. The architecture of CCTP is shown here. It combines the prediction model Gaston with two transfer learning methods, parameter transfer and gain-based domain adaptation. A mapping function M is used that maps each region from the target to the source city. After mapping, all regions to the target would be automatically grouped into the corresponding cluster. The DTW algorithm calculates the traffic pattern distance between each target region and a source region. Accordingly, all regions in the target city are further split into C clusters. To address the domain shift problem, a cross-domain adapter leveraging a GAN to generate ample realistic samples is proposed. GAN consists of two neural network models, a generator and a discriminator. G learns the distribution of real data and generates fake samples that look real and can fool D. D tries to distinguish real data from fake data, and they are trained simultaneously via an adversarial process. GAN will reach convergence when the fake data generated by G is indistinguishable from D, indicating that G can produce a good approximation of the real data. For this study, the generator are modified by treating a target sample as input of the generator. Instead of feeding a noise sample, the generator G is combined with Gaston, which uses the output of G as its input and then provides guidance for gain training. Here, the trained CCTP model can be transferred to the second cluster as its initialization, and then the second cluster only needs to fine-tune the model with its data samples. This avoids the second cluster learning from scratch, and it is of great benefit for clusters with a small set of training samples. It can be used to transfer knowledge among clusters in the target city. CCTP find neighbors for each region in the cluster to promote traffic prediction. Pre-processing. In figure 9, low demand can be practically neglected, so only regions with high demand in the two cities are picked. 900 regions are selected from Milan and 414 scattered regions with high demand traffic in Trentino. Milan's data will be treated as the source data and Trentino's data as the target. LSTM is adopted as the network in CCTP to capture the sequential correlation. The hidden unit of each LSTM is 64, weight 0.8. Adam optimizer and early stopping are adopted for model training, and CCTP can converge within 100 epochs to determine the number of neighbors for each region in both cities. The average DTW distance for all regions with their nearest neighbor is calculated as depicted in 10A. It can be seen that the average DTW distance grows rapidly within the first 200 nearest neighbors in both cities, while maintaining similar with the following 21 to 50th nearest neighbors. 10b provides the cumulative distribution function of the number of neighbors for a node when k is 15, which shows that different nodes can have a varying number of neighbors. CCTP performance can be evaluated by comparing it with the two types of baselines. Training samples were collected only from target Trentino city. Transfer learning approaches using both source and target data. For a fair comparison, the spatial temporal methods in the two baselines consider spatial correlation among 5 by 5 adjacent regions. Thus, each region has 24 neighbors, which is the same as the setting in CCTP. Evaluation metrics. The following evaluation metrics are employed. Smaller the values of these metrics indicate more accurate prediction of the model. The key parameter to influence the prediction performance is C. In 11A, the daily mobile traffic volume in different regions of Milan exhibit great diversity, indicating that purely training one node RNN module in CCTP would fail to capture the volume dissimilarity and further degrade the prediction performance. Hence, extensive experiments were conducted with different choices of C. 11B shows that taking RMSE, the prediction performance improves when C increases from 1 to 3 and degrades with a bigger C like phi, because C determines both the number of node RNNs and the number of training samples for each node RNN. A smaller training dataset leads to performance degradation when C is 5. More clusters in CCTP increase model complexity and training time, so C is fixed to 3. Table 1 shows that CCTP significantly outperforms all the baselines, achieving the minimum error for all three metrics. Table 2, when the target city holds one-day mobile traffic data, CCTP outperforms. This indicates that the knowledge learned by Gaston from the source city is valuable for transfer learning even when the data transfer is extremely scarce. The performance improves as the number of days of mobile traffic series available grows. The CCTP consistently outperforms the best baseline. Figure 14 shows the evaluation results. CCTP PT performs better than Gaston, indicating the effectiveness of GAN. However, comparing CCTP PT with CCTP, we saw that applying the domain adaptation technique is not enough, and it is necessary to adopt inter-cluster transfer learning for superior performance. Also, the result shows the significance of inter-cluster transfer learning, as the performance of CCTP DA is dramatically superior to the pure Gaston. However, CCTP DA cannot get the best results as it lacks domain adaptation. On comparing the performance of CCTP DA with CCTP, we conclude the proposed domain adaptation method implemented by GAN is valuable. By integrating parameter transfer and domain adaptation into Gaston, the proposed CCTP achieved the best performance. Figure 15 shows a visualization of error maps of Gaston, CCTP PT, CCTP DA, and CCTP. The error maps calculated by absolute error reveals that CCTP enables inaccurate citywide mobile traffic prediction, while the prediction error of its variant are relatively large. In this slide, we'll explore related work done on the two main components of this paper, mobile traffic prediction. Earlier, traditional statistical models like support vector regression and ARIMA, autoregressive integrated moving average, were widely used. Recently, deep learning approaches have taken over them. Example, RNN, which is proposed to handle sequence data, LSTM, long short-term memory, a special kind of RNN capable of learning long-term dependencies and preventing gradient vanishing. Many other studies explored were CNN-based methods used for capturing special dependencies are only available for the data with regular grid structure in space and are difficult to generalize data with an irregular spatial structure. The proposed model is purely based on RNN modules which extract special temporal features simultaneously based on a graph structure without the need for a regular grid structure. Transfer learning, since it is expensive and time consuming to rebuild a model for new training data, transfer learning is used. It is composed of three methods: parameter transfer, domain adaptation, multitask learning. In this paper, the method of parameter transfer and domain adaptation are combined to achieve effective transfer learning across cities. The proposed CCTP framework was able to achieve accurate traffic forecasting for a data scarcity. Efficient prediction model Gaston integrates temporal factors and spatial dependence based on the graph structure constructed by the similarities among the region. Two transfer learning strategies proposed to achieve superior prediction performance for a data scarcity outperforms other state-of-the-art methods. The feasibility of a transfer learning approach for intelligent network management and resource allocation across different entities like base station with distance service demands can be explored. Thank you.